Oh crap! I should have studied that schematic. Was it red or yellow or blue? Yellow or blue? Yellow or blue? Come on, I can't remember. Let's just try both. Looks like that was just a nightmare. So, we're back at the PDSSAP 20 B2 version with our sleep timeout problem. So today we're going to be looking at how to fix that. So I've taken the tool apart, as you may have seen in the previous teardown video. You just have to pull out the Phillips screws on the side panel and the 4 hex head screws on the impact drive, and then after cracking some factory super glue, just gluing these two parts together on this edge, this should just pull off. And here we have full access then to the wiring of the tool. And as you can see here, it is using our fairly recognizable FA2-16/1WEK QIANHE trigger module. So this is a module you'll find in fair few of the Parkside Performance tools. In this application here, it has 6 wires going into it, and here it is connected via a connector to the control PCB for the brushless motor. So here we do have a bit of Celastic keeping this connector in. If you get into there with an X-Acto knife or a scalpel, you can sort of break that adhesive, and then you can fairly easily pull off this connector and also pull off the switch or the trigger module. Just make sure you disconnect it from the directional switch, and then you have a fairly easy access to the setup here. So we have our connector with 6 pins on, or 6 wires connected to here to the PCB, and another 6 wires connecting into here. And you can also see here it's actually nicely marked wire 1 to wire 6 here, so it's fairly easy to follow which wires need to be processed for this hack. So actually I've had another of these trigger modules hanging around that I managed to disassemble. So as you can see, it looks exactly like this one here, except that I've pulled the red trigger off. It's just friction fit, and there's a little rubber boot on here. Around the outside perimeter, we have these 7 clips, 2 on the top, 2 on the side, 2 on the bottom, and 1 just under the trigger here. Just in here, and if you carefully pry those with a sharp sort of pin, any sort of disassembly tools, you can crack open those latches, doing maybe a little bit of damage to the plastic clips, but most of it should come off fairly unscathed, that you can reassemble it. As you can see here, there's quite a bit of marring where I've picked at that, but eventually you are able to split it open, which gives you the inside of this trigger module. So as you can see here, it's all falling apart since I've desoldered it. We have our little PCB board that is soldered onto these 3 pins on here, and underneath this board, where you can see we have some contacts, we have these sliding sort of little copper fingers that when you depress the trigger, they move. So this is the inside of the trigger. Here we have our bottom contacts, here we have our center contacts, and these 3 contacts go to the directional switch, which just sort of clicks in and out here. And if you're not too careful, it'll also just fall out with this sort of sprung metal piece. Be careful you don't lose that, that can fall off. So this just goes back into here. You just have to sort of push it down with something. Don't really have anything too handy, but just sort of push that spring in. See if I can replicate it on here. Yep, and it should pop back into its home. Then you have these 3 pins that you have to desolder to get the board off. The best procedure I found is just to flood all 3 of those pins and then quickly try and pull this off. Make sure you don't lose either the spring that's connected into the trigger here. There's a little plastic stock preventing that spring from bending inside it, and these 2 copper finger contacts that are just sitting in the trigger assembly here. So once you pull this board out that's sitting just like this inside the trigger module, you'll see that your 6 wires will be connected to these pads that are actually numbered nicely 1 through 6 on the bottom here. Now, if we flip this board onto the other side, we can see that our main functional contacts are on this side. So we have our 3 contacts to the directional switch on top here. Then we have this resistive carbon track on here that will be setting the rotation speed of the brushless motor. And then we have this long, fat, discontinuous track on the bottom, which is involved in the safety or the sleep mode. So I've drawn a little schematic here that should help us understand how this switch works. So if we have a look here, we have basically the same drawing of these contacts on here, and the numbering here follows the numbering of the wires, 1 on the left, 6 to the right, as is indicated on the board. So pretty much what we have here is the top directional contacts, the left one and the right one here, that goes to wires 2 and 3. So this is wire 2 and 3 here. Then we have our copper track, that is the top one here, and the carbon coated one on the bottom there. And then we have our wires that connect to these outer 2 contact surfaces on the bottom of the board, which basically just tell the PCB when the trigger is being pulled in more than half, or 75%. So as you can see on this trigger assembly, this is pretty much going into this like that, and you have the wires soldered onto these pads. They have sort of different colors, right? But unfortunately, the colors that I've marked here, they do fit my particular switch, but these wire colors are not following the pin numbering. So the sequence of colors doesn't follow the contacts pin 1, pin 2 through 6. The assembly workers, they just grab 6 different colored wires. They just make sure that pin 1 on the connector connects to pad 1 on the PCB, but the color isn't representative of the position. So if I tell you, okay, you have to do the yellow and green wire or something, you actually have to go for the numbered position. Don't go by the colors, since they are fairly random, actually. So the way this switch works, I'm just going to draw it in here. So we have our directional switch. Contact number 2 is VCC from the PCB, and VCC is also present on this pin here. So everything where it says pin 2, which in this case happens to be the white wire. So we have VCC on pin 2. Now, to control the direction on this switch, as I had shown you earlier, one direction is just pin 2 and 3 open, and for the other direction, when you flick the switch, they are connected. And I believe in neutral it's also open. So let's say counterclockwise is open, neutral is open, and clockwise is just pin and 2 connected together. So then we have our second control system, which is to control the speed. So the way this works, we have our little single file copper finger here, and it basically just connects right over these 2 pads or tracks, and connects in the way I've drawn on here. So since we have VCC on here, and we have pin 1 to ground, basically, this forms a voltage divider. So this full resistive carbon track, as I showed you here, the black one, is about, I think, 57K resistance. So when you have VCC and you have this sort of sliding contact, it basically forms a rheostat and a voltage divider. So the voltage that is transferred via the copper fingers to this track that's connected to wire 6 is a changing voltage depending on the position of the sliding contact. So at this position, we have a small resistance, let's say 10K here and 47K here. So this voltage will be small. And if we have this position here, where here we have 10K and here we have 47K, this will be a high voltage on this pin. So pin 6 is a varying voltage that just tells the PCB what speed to turn the motor. And then we have our final connection, which are these contacts you see here at the bottom. And the way the copper connectors or contacts are made here is that they sort of grab both sides. So what they are doing when the trigger is not being pulled, we basically have this kind of configuration of contacts. So it's just connecting wire 4 to this non-connected center pin. But as you push the trigger to, let's say, 75%, you have this contact bridging over to the edge here. And then we do have connectivity between pin or wire 5 and this pad 4. So only once the trigger is sufficiently pulled do these two pads intersect and get connected, and that signals the PCB that the trigger is being intentionally pulled, and that is the logic element that indicates to the PCB if it should be going to sleep or activating its safety overload, whatever mode, where it turns off, goes to sleep, and requires that full trigger pull to reactivate again. So the simplest way we can hack this situation is we permanently give the PCB this signal that the trigger is being pulled. Since this bottom track doesn't have any effect on the speed the motor is turning, we can just short wires 5 and 4 together constantly and not have any defects on running the motor. So we have our two wires running here. The easiest thing would be just to cut them off here, solder them back together, and have them permanently connected and indicating, yes, the trigger is being pulled. It will never enter sleep mode, and it works perfectly fine. The only issue with this here is that we might have a problem with sort of current draw, that it never goes to sleep. So as I'll show in just a moment, if you just connect these two wires together, you'll have the desired quick reaction on the trigger, but you'll also have a problem with the LEDs being lit. So the white illumination LED, it will actually turn off after its like 10-20 second timeout, so that isn't a problem, but your little green torque LED will remain lit all the time. And I've measured the current draws here, so when you have the non-hacked version, so no hack and hack, we have our sort of on state, which is 42 milliamps in both situations. Then we have our sort of half asleep state, where we have our torque LED on, that draws 26 milliamps. 26 milliamps in both states. And we have the tool asleep or off, which draws 0 milliamps in this state, but since we're giving, in the hacked situation, we're giving it the awake signal, it is still drawing 26 milliamps by lighting the torque LED when otherwise, without the hack, the device would be in the sleep state. So 26 milliamps isn't that much current. It'll take, I think, 3 days to discharge on the 2 amp hour battery, 6 or 12 days respectively on the 4 and the 8 amp hour battery. The thing is, if you're used to having the tool just sitting on your bench with the battery connected, you'll have to, disconnect the battery when you're done with the tool. If anyway, when you use the tool, you take the battery off to charge it and you just leave the tool without the battery, you won't have any problem having this hack installed permanently. One option you could also do is, instead of just cutting these wires 4 and 5, you can actually just install a little micro switch here. So leave them connected to the board, install a little micro switch like you would either something like this, where you can sort of flick it on and off, or install a latching. I know this is just a momentary micro switch. Install a latching micro switch. Somewhere in the body, there's plenty of space here. If you would drill a little hole here and place your latching switch or something like this in the side, you could toggle this hack on and off just via that switch. So when you're using the tool, you close the switch, the hack is on, the tool responds instantaneously. If you go to set it to the side with the battery still installed, you can just open this switch here and it will go back to its 0 milliamp hour sleep. Again, 26 milliamps, the green torque LED stays lit all the time. Maybe if your usage case, you always take your battery off, this is no problem. If you want to go more advanced and put a switch in, you have the option to do that. So now that we've seen how all this works, let's actually apply this hack and see how it works. So here we have our torque switch. As I said, we're going to be cutting wires 4 and 5 here. So that is, following the, let's see here, the numbering on the switch here. So we have 1 through 6. So we're going to be cutting the yellow and blue wires. Wow, why are these already cut? This makes no sense at all. Whatever. So we're going to be cutting wires 4 and 5. In my case, these are yellow and blue. In your case, it will most likely be a different color, so make sure you count wires 4 and 5 either from this glued end, or if you go to the connector here. So in my case, the black wire is pin 1. So on one side of the connector, it's just fully white. There's no windows. On the side where you have these little fingers and you can see these metallic windows, the leftmost wire is wire 1. The rightmost wire is wire 6. So in my case, the black wire is wire 1 and the 6th wire is the green wire. You can see that just on the back side. This is the front, pin 1, pin 6. So here we've already cut the yellow and blue wires, which are 4 and 5. And we can proceed to strip and solder them. I'm not going to do a very detailed job of this. We're just going to do a quick and easy sort of hack. We can pull off the insulation we have here. We need to pull off the corresponding insulation on the other side. Meanwhile, we can get our soldering iron up to temperature. We don't actually need to worry about those other sides. We're just going to solder these two wires together, and these two you can just leave flopping in the breeze there. They aren't going to be doing anything at all. So now that we have our two little wires together, let's just apply a little bit of flux here. If you're ever using these flux syringes and you have a hard time pressing them down, this is a very nice 3D printed sort of dispenser. As you can see, we can get our flux out. You can find a link to the 3D model in the description of the video. So now that we have these nicely fluxed, our soldering iron is up to temperature. Let's see if we can coat these with solder, and doing a very bad soldering job Let's just blob those two together. Perfect. No need for any heat shrink, no need for any sort of extra care. We have soldered those two wires together. If you were installing a switch, you just peel back the insulation and install the switch between the two wires. So something like this, I guess. In this case, we're just going to do the easy fix method. So let's reinstall this here. And I will get back to you in just a second once I've gotten the tool all back together. So here we have it. The tool is fully reassembled. We have our bolts stuck into place. So this is the moment we've been waiting for. Let's put in this fully charged battery and see how our tool performs. So we should have the wake up connection permanently closed. So immediately we should see our torque light come on without needing to press the trigger. So here we go. And there you have it. We have our little torque LED immediately come on. Let's try the trigger. So remember, before with the sleep mode on a new battery, the first trigger pull would have to be extended to wake up the tool. Let's try this. Tool comes on instantaneously. So tool is back working as expected. Our illumination LED comes on as is normal. We'll see it will also turn off when we leave the tool idle like this. As you can see, tool has turned off. Our torque LED still remains lit and it will never go out. So the way we have it now, if we had the old working mode of the tool, after 40 seconds, this torque indicator LED would go out, the tool would enter sleep mode, and it would require a solid trigger pull to wake it up. Now that we've bypassed that sleep mode, basically trigger connection or contact point, the tool stays permanently awake. So it is wasting the power to illuminate this torque LED, which is about 25 milliamps. That probably includes both the LED and just some basic running of the control board, but I expect the quiescent current of that should be super low. So mostly this LED, and it will never go out. So now 40 seconds have certainly passed. We go back to the tool and we have immediate responsiveness on the trigger. So as you can see, the tool works. That was highest torque. It works in the low speed regime. We can turn it back up. So the RPM selection works without any problems. Our trigger is as responsive as ever. There is no deterioration to the function whatsoever. The only thing that we lose is the power down sequence to cut battery drain to 0 once it's in sleep. So now that you've performed this hack either just by cutting and soldering the wires or maybe installing a little toggle switch here on the back, when you are in the no sleep mode, your battery will constantly drain power. So what you have to keep in mind then, once you've performed the hack, every time you're done with your tool, you have to disconnect the battery. Ideally, you do this anyway just to set it to charge. If you leave the tool on the battery, it will take anywhere from 3 to 12 days, depending on the battery capacity, to actually fully discharge. So even if you leave this out on your workbench for maybe a day or two, it will not totally discharge your battery. Even if it does go to the full discharge, it won't damage the battery, since the internal protection will kick in and will protect the battery from being pulled down all the way to 0 and damaging the lithium. But just be aware that with this hack, you will have the constant battery drain via this torque indicator LED that constantly stays lit. But we have solved our main issue of our sleep and shutdown mode. So anytime you are pulling any massive amount of screws and maybe doing some pauses in the work in between, this fix will certainly help with that. So I'll be back in the next few days looking at how to apply this fix to other tools in the Parkside Performance lineup. since many of them share either the same or a similar trigger module, this type of fix is applicable to those with a couple of adaptations. So thank you for watching this video until now. I really appreciate your support. We're closing in on 1,000 subscribers. So if you enjoyed this video and would like to show your appreciation, please hit that subscribe button, like this video, and that will also give me a signal to dedicate more time and effort doing this type of detailed reverse engineering, doing these type of teardowns, and being able to come up with new hacks of this type in the future. So if you want to support the channel, hit that like button and hit the subscribe, and let's make it all the way through 1,000 subscribers. Thanks for watching, everybody. See you next time. Bye-bye.